Hello. So we're moving on to our next chapter, next section, and this is going to be covering chapter 2.7, and this is inverse functions. We're going to be talking about inverse functions. Okay. So what is an inverse function? Let's go back, very basic. Let's talk about a function. So here you have a domain, here you have a range. Inverse function, or not inverse function, a function takes elements from the domain and maps them to elements in the range. So here, f, this function maps x, elements in the domain, to these elements in the range, f of x. So it takes them and maps them, okay? So maybe we're taking the numbers 1, 2, and 3. We're mapping them to 0 and 3. All right? So it could be like taking, we have 3 cities and we're mapping them to population sizes, right? Or so you could be taking your domain as cities, your range as population sizes. You could say various different other ways of doing this, but basically you're taking elements from the domain, mapping them to a range. Now, what an inverse function is what happens if you want to go the other way. What if you want to take, like we took cities and mapped them to their population size, what if we listed a bunch of population sizes and we want to map them back to the cities? Okay, well, that's called an inverse function. It's mapping, so inverse function, it's mapping from your previous range to your domain in the original. Okay, so it's going to take the elements of the range and it's going to map them to the domain backwards. So if you want to go backwards, if you want to return, if you want to say find all the cities that have a population of 10,000. So you're saying plug in 10,000, return name of cities. Where previously it was you plug in name of cities, return the population. Now, this runs into a problem. Okay. The problem is functions, if you remember, they're only one element in the domain every element in the domain maps to only one element in the range. Not meaning that they all map the same, but there isn't like, you don't have a scenario like this. This goes back to our boys and girls. Boys and girls. All right. So we took names of boys. Say we have Bob, Joe, James, John. And we're mapping them to their girlfriends over here. Okay. We got Tammy, Diane, Courtney, and Sue. Well, let's say we have this mapping, this function maps Bob to Tammy, Joe to Diane, James to Courtney, and John to Courtney, and then Sue doesn't have a boyfriend. Okay? This is a function, this mapping. This is an f of x, because each element in the domain, all the boys, are only mapped to one girl. They're not dating 2 girls. They're only dating 1 girl. It doesn't matter that Courtney is dating 2 boys. The functions only have, it only is worried about the domain. It's a restriction on the domain. Well, unfortunately, we can't then have this inverse function, because this inverse function is the girls are going to become the domain now. And then we're going to map them back to the boys. So we're now switching, so the girls are now the domain. And right off the bat, we have 2 problems. Courtney, if the girls are now the domain, Courtney has 2 boyfriends, and part of being a function is you can't map one element from the domain to 2 elements in the range. And the other problem is Sue. The other restriction on functions, every value in the domain has to be mapped. And Sue isn't mapped at all. She doesn't have a boyfriend at all. So we run into those 2 issues here. So this function, even though it's a function originally, you can't create an inverse function going backwards. Okay, so that's the first problem is that not all functions can you create backwards. We have a function going this way, f of x. We don't have an inverse function going backwards in this one. We have no f inverse, okay, because it isn't a function. So that's what you run into, is you have to ask yourself, is my original function, is it invertible? And not all functions are invertible. Okay, a function is it's invertible if it has an inverse, if it follows this rule. F of f inverse of x returns the x values. So here we're taking f inverse of x, or f inverse of f of x also returns the x values. So here, bottom one's a little easier to explain. These are your y's, these are your girls. You're taking the girls and the f inverse is mapping them back to the boys. So this outputs boys. Okay, so here is boys. Boys, then the f gives you girls, and the f inverse takes girls and gives you back boys. So this one, it's taking, here's boys, or, yeah. Okay, the top one's a little harder to explain, but basically, this is another property of inverse functions, are that if you compose a function and its inverse together, you're going to just return x. You're just going to return the domain. Okay, that's the definition of an inverse. Not all functions have inverses. Okay, and let's then look at when they do and when they don't have inverses. Okay, so easiest way to look at it is to look at pictures. So I've drawn these are all functions. All these pass the vertical line test. So they're all functions, right? They pass the vertical line test. Now the question is, do they have inverses? Well, inverses means that if you map from the y to the x, your y values each y value won't have two x values or more. So here, if we look, I'll do this in red. Here is this y value. It is mapped to two x values here. So this y value, if you go backwards, it would fail. So this parabola here does not have an inverse. And notice it fails what's called the horizontal line test. So another way, if you have a picture, is do what's called a horizontal line test. If a function fails the horizontal line test, it doesn't have an inverse. So if it fails horizontal line test, has no inverse. Okay, and of these functions, you see the parabola here, which is f of x equals x squared. It does not have an inverse. This one right here is f of x cubed. It does have an inverse. See, no matter what horizontal line, it only crosses once. This one does not. It fails because of there. I drew a horizontal line. This will be f of x equals maybe x cubed minus an x squared or something like that. So it's a mixture of x cubed and x squared. And then the last one is a linear, and linear passes both. Okay, so this is your f of x equals mx plus b, right? And linears are invertible. Okay, which kind of tells you general equations. So if your function is even, if you're having even powers on your function, then it's not invertible. Okay, not directly. So notice here, this guy was not invertible. It had an x squared. This guy was not invertible, and it was because of the x squared. In general, if your function is odd, if your polynomial function, let's just talk about polynomial functions for now. If your poly is odd, then it's invertible. If it's even, if your poly is doing double is even, it's not. With the exception of a constant. This is with the exception of constant. Okay, so I know technically your line, the b, if you have a constant term, that makes a function neither. And so ignore the constants. If you have a constant, yeah, then you have to, if you have a constant, you have to look at things. It can do some weird things. But these are just general principles. If you just have like, yeah. All right, let's just ignore that for now. It's getting too complex. They're not going to ask you to do that anyway. What they're going to do, so I'll just show you a bunch of other ones you can tell. So we already did f of x equals x squared, and we know it's not invertible. We could do f of x equals x to the fourth. It's also a parabola. It's not invertible. In fact, any f of x to the x to the n where n is even is not invertible. However, f of x to the x cubed, we noticed was invertible. It looks like this. And you're going to find any f of x to the x to the fifth will be invertible. So if f of x to the x to the n and n is odd, those are invertible. And with square roots, again, square roots can be, this was just dealing with polynomials above. Square roots can be sometimes they can be inverted. Like this guy, this is just your regular f of x equals square root of x. It can be inverted. And we'll look at those, we'll invert those. In general, if they give you a picture, it's easy to tell if something's invertible or not. Sometimes it's a little harder with an equation. You often have to graph it before you can answer that question. So now let's talk about how to find the inverse. Well, finding the inverse is fairly easy. The procedure for finding the inverse what you do is you have f of x equals stuff that's in terms of x. Okay, what you do is you switch x and f of x, and we'll call f of x y here. So define and then solve for y. So if we take a linear, which we know has an inverse, I already told you all linears have inverses, and what it's asking you to do is switch them. So we're going to rewrite this as x equals 7y minus 5. So just renaming the variables. Okay? And then we're going to solve for y. Now solve for y. When you solve for y, you're going to add 5 to both sides, right? So you're going to x plus 5 equals 7y, and then divide by 7. And you get y equals x plus 5 over 7. And this will be your inverse. Inverse function of x is x plus 5 over 7. That is your inverse. Let's see if it actually works out. Remember, the definition of an inverse is if f of f inverse of x equals x, right? And vice versa, both directions. Well, let's plug f inverse into the original function. So if we plug this guy here into this here, let's see if we get x. So now you plug them in. So you got 7, and then you have your x. Your x is now x plus 5 over 7, right? Because So I plug that into x minus 5. So here's this guy here. Now watch what happens. The 7's cancel. Then you're going to have x plus 5 minus 5. The 5's cancel. What do you end up with? Sure enough, it's an inverse. Okay? So that's a simple procedure for finding inverses. Let's look at some other ones. Here is a function. It does have an inverse. It's odd with a constant added, which is fine in this case. Let's find it. So we're going to switch them. So it's going to become x equals y cubed plus 1. Now what you do is you subtract 1 from both sides. X minus 1 equals y cubed. Then to get rid of the cube, you take the cube root of both sides. And you get y equals cube root of x minus 1. Oops. Okay, that tells you the inverse is cube root of x minus 1. We could check it by plugging this guy into the x function in your original. And when you do, what'll happen is you'll have, here's your cube, that's your x plus 1, that's original. We're going to replace the insides of the x with this, right? And what's going to happen then is these are going to cancel. That'll give you x minus 1 plus 1. Those cancel, and you're returned with an x. So then indeed it is an inverse of the original function. Okay. Last but not least, let's look at a rational. So now we switch them. So you're going to have x equals y plus 2 over y minus 3. Now you're going to have to solve for y. Okay. Now this gets a little bit more involved when you're doing this, solving for y. So I need to clear out the denominator, so I'm going to rewrite it as x y minus 3 equals y plus 2. So I multiply both sides by y minus 3. I'm going to FOIL this out. Xy minus 3x equals y plus 2. Then I'm going to move all my, first thing, let's go through this again. So the first step I did was I switched my x's and my y's. I did that here. Okay. Then I took this guy and I multiplied it on both sides. Okay. So I took y minus 3, multiplied on both sides. On this side it cancels, this side it becomes here. That's what I got there. Then I distributed, okay, did that there. Now what I'm going to do is now I'm going to move all the y's to the left-hand side, everything else to the right. So I'm going to leave the xy on the left hand. I'm going to move this y over by subtracting it. You get minus y. I'm going to move the 3x over by adding it. You get 3x plus 2. The 2 remains. So I just moved everything that has a y to one side, everything that doesn't to the other. Now what you're going to do on the left-hand side is you're going to factor out a y. Factor the y out. Okay. The last step is divide both sides by x minus 1. And you get y solved by itself, which was the whole point. Okay. And that'll be your inverse. Notice your inverse has a restricted domain, different than your original. The original couldn't be 3. On this one, you can't be 1. Okay. And that happens. But other than your restrictions on your domain being different, you can plug it in and you will get x when you plug it in. It will require more math work, but that's the inverse. So f inverse of x equals 3x plus 2 over x minus 1. Okay? Last part of this chapter, so is what about when given a graph? Okay, how do you find the inverse? So we're going to look at that. We're going to start with a simple graph like this. Well, what an inverse is it's going to take, okay, and it's going to take any point, like here, let's say here is 0, 1, 0. All right, and what you're going to do is you're going to change them. You're going to switch your x and your y. That's what an inverse does. So it's going to switch. So if the original one, this point here was 1, 0, on your inverse function, which I'm going to do in red, you're going to have the point 0, 1, which is there. And then if you have the point here, let's say this point is 3, 2, then up here you're going to have the point 2, 3. All right, so this point, start here, this point will be the point 2, 3. It's going to just switch it. So that's what you do with an inverse, is you're going to map out all the points and switch them on the inverse. Okay, so it's fairly easy to do. Another example would be, let's say you had this line here. Now lines pass through 2 points, so you only need 2 points to draw a line. So all you're going to do is invert these 2 points. So this point, it is, if this point is say 0, 2, then the other point will be 2, 0. This point here is 3, 0, then that point will be 0, 3, and then you'll have your inverse passes through those like that. So you just switch them and graph them. Okay, and you can do that with, even if you have a function that does something like that. All you really need to do is just graph these points here and take another point there. So these points, so if this point's AB, then you're going to graph over here somewhere BA. If this point is CD, you're going to graph somewhere over here DC, etc. This point is MN, you're going to graph somewhere over here N, comma N, right? And then you'll end up with a weird looking inverse that will be the inverse of the function. Okay, so what about, let's go back to the parabola and talk about it briefly now. So here we have a parabola, and this is, other than being an ugly drawing, what is the inverse of this? We already know it doesn't have an inverse because it fails the horizontal line test. What you can often do with these is maybe you really do need an inverse of this x squared, but you're only interested in when x is, say, positive. You're not interested in the negatives. So if you're going to restrict, so what they're going to do sometimes with even functions is they'll limit the domain. And they'll say, okay, we're going to ignore everything down here. Well, if that stuff is gone, if we limit our domain to 0 to positive infinity here, then the function passes the horizontal line test, see? Because this stuff over here is gone. We're only looking at this part of the graph. So they restrict the domain, and then they find an inverse. And so you'd still do it the same way. If you want to actually find it, you'd switch it. So this would be x, this would be y squared. You're going to solve for y, which will give you square root of x equals y, right? But you normally put plus or minus, which is why it fails. Because then you have f inverse of x equals plus or minus x square root of x. So it fails there. But we already restricted and said we weren't interested in any negative values. So we ignore those, and now we have an inverse. And you could draw it. What's going to happen here is if you look at the diagonal, and you're going to end up with an inverse that looks like that, passes through the diagonal. Okay? So that's how you can find, if you limit the domain on an even function, an inverse. All right.